All right. Let's review a little bit of what we talked about last night. Hold on, let me take a picture of this. Okay. And use black. I'm going to give you some functions, and I want you to tell me what transformations are being done. Okay?
Okay.
About that one. First of all, I want you to tell me the parent function and then the transformations that are being done.
Okay.
The parent.
The parent function is y equals x squared.
Okay. What's being done? And incidentally, the way you find the parent function is to get rid of all the transformations. In other words, that's a transformation, that's a transformation, and that's a transformation. So when you get rid of all three of those, you end up with the parent function. So if ever you have a hard time figuring out the parent function, that's the way you do it. Okay?
Okay.
So there's three things going on. What are they? Describe them for me. Let's go left to right. What's this first minus sign do?
It's a vertical translation?
Reflection.
Reflection. Okay, that's the one that I always mix up.
Okay. Well, just remember that leading minus signs or minus signs in front of the X, they're either vertical or horizontal reflections. A vertical reflection is a reflection over which axis?
The y.
Oh.
X, gosh, okay.
Yeah. Let's say I was reflecting that function right there. Vertically. Okay?
Okay.
Take your hand and flip that over the x-axis, and it becomes that, correct?
Yep.
You see why that is a vertical reflection, why I call it a vertical reflection.
Yeah.
Okay. If I was going to do a horizontal reflection, it would look like that. In other words, if I take my hand and put it on that function and flip it to the left, that's horizontal. So horizontal reflections are over the y-axis, vertical reflections are over the x-axis. And most school systems, they don't want to know vertical or horizontal. They want you to tell them reflection over X or reflection over Y. Now, the reason I call it vertical is because it helps categorize all of these transformations. There are three transformations that are vertical, and there are three transformations that are horizontal. And they all have the same characteristics. If the numbers or negative signs are outside the function, then they're vertical. If they're inside the function, they're horizontal. Okay? So what's the 2 do?
It is a vertical stretch by 2.
Perfect. By a factor of 2. In other words, vertically stretched by double. And finally, what's the minus 1 do?
It's a vertical shift down 1.
Good. Down 1. And notice that that's outside the function, that's outside the function, and that's outside the function. Now I'm going to give you a similar one where everything is inside the function. Hold on. Now let's do just this one first. These can get a little complicated. What's the minus 3? Well, first of all, what's the minus 2?
It's
Vertical or horizontal?
horizontal.
Okay. Negative signs are always what?
Reflection.
Okay. So it's a horizontal reflection over which axis? Did you say the Y?
Yeah.
Or audio? Okay. What's the 3 do?
It is a horizontal shrink.
Very good. It's the opposite of the vertical ones. In other words, because the 3 is greater than 1, and I don't mean minus 3, I mean the 3 is a number greater than 1, then it's a shrink if it's horizontal. If it was vertical, it would be a stretch. But it's a horizontal shrink by 3, or really a factor of 3. And finally, what's the plus 2 do?
It is a horizontal. Wait, vertical.
Is it inside? Yeah. Is it inside or outside the function?
Outside.
Okay.
So it's a
That makes it vertical.
Shift up 2.
Good. Now, the one thing that I haven't put up there, here, let me give you an example of one. I didn't want to confuse the issue. That's a negative sign in front. In other words, what I meant to write was this. And notice, well, you tell me there's two things going on. What are they?
There's a vertical reflection.
Okay. So that means, in fact, you don't even need to say the word vertical anymore. That's just kind of my way of categorizing it. They won't use that word in your math class. They'll say reflection over which axis?
Over.
Think about a function. Think about something that looks like that. If you vertically reflect that, which axis are you reflecting it over?
Yeah.
Okay. That's how you want to think about it. Just draw something in that first quadrant, that being the first quadrant, and you're either going to reflect it into the lower quadrant or the quadrant to the left. And if I reflect it to the quadrant to the left, that's a horizontal reflection over the y-axis. If I reflect it down here, that's a vertical reflection over the x-axis. What else is going on up here? One other thing.
Horizontal shift to the right.
Good. To the right by 3 units. Very good. So, let's see if we can graph that. What would be the first thing I'm going to do if I try to graph it?
Isn't the first point 0, 0?
Well, the best way to graph these is to graph the parent function first. So what's the parent function look like? Y equal x squared. What does that look like? What's it called? Where's the vertex?
I'm pretty sure it's at 0, 0. That's the vertex.
That's the vertex, and it's a parabola. So that's the graph of y equal x squared. Okay, now let's go through each of the transformations in a different color. Which one do I do first?
You do the reflection.
Always do both reflections first if there are two. If there's only one, do it first. The order that you do everything else does not matter, but you must do your reflections first. So that's my vertical reflection, right?
Yep.
Okay. And now in green, I'm going to do a horizontal shift to the right by 3 units. Does that change the shape of the curve?
No.
Just moves it. That's why it's called a shift, as opposed to a stretch or a shrink. So the green curve is the graph of this. And that's the way you want to graph them, is start with the parent function, and then just do every transformation, even if there's all 6. In other words, you can have functions that have all 6 transformations in a single function. Now, let's consider a couple of other functions. Think for a second. It's the parent function.
Y equals x, the square root of x.
In other words, all you have to do is remove all of the transformations and you got the parent function, pretty much. That's the way to really think about it. Okay, and that looks like this. I'm going to draw that over here. That's what that graph looks like. Okay.
How do you get that, though?
I just have it memorized. In other words, there are like 10 elementary functions. Let me list them, as many as I can think. You got y equals mx plus b. That's a linear. Y equal x squared. That's quadratic and a parabola. You got y equal x cubed. That's a cubic. You got y equals square root of x. That's an elementary function. You have y equals sine x. That's an elementary function. You have y equal cosine x. Have you had any trig at all? They give you any at all?
No.
Okay. Well, let's ignore these trig functions then. But that's some of the trig function, elementary functions. Okay. Now, let's get back to this square root function. In other words, I know what each of these looks like graphically. So, because I deal with them all the time. But it wouldn't be a bad thing for you to memorize either. And by memorizing, I mean memorize your elementary functions. Okay, and what they look like. Because then you can graph any function. Now, let me add something to that. Hold on. First of all, if you don't know how to graph a function, there's an easy way to do it. When you said, how did I know how to graph that square root function? Well, let's make the most basic way to graph a function. Make a table of x and y values. When x, this is my parent function, x is 0. The square root is 0. Baby, you still there?
Oh yeah. It just cut out.
Yeah, I noticed there's a little bit of audio interference here. So when x is 0, what's y?
0.
When x is 1, what's y?
1.
When x is 4, what's y?
2.
So all of these points are on this curve. In other words, there's the 0, 0. There's the 1, 1. And there is the 4, 2. So even if I did not know how to graph y equals square root of x, is all I got to do is make a table and plot these points. Plot the x coordinate and the y coordinate. And you end up with what the graph looks like. Okay?
Okay, thanks for explaining that.
Yeah. That's the hard way to do it, though. You don't want to have to be making tables every time you want to graph an elementary function. Far easier to memorize what the graph looks like. The basic graph. Okay? Okay, so now I got 3 things I'm doing to this function. What are they?
There's a vertical reflection over the x.
Let's do that one first. And if you don't understand on how I do these reflections, be sure and stop me. In other words, that's what a vertical reflection of the black line looks like.
Yeah, I got that.
Good. Okay. What else? What's the 2 do?
It is a vertical stretch
Okay.
of 2, of the factor of 2.
By a factor of 2. And what that means, if I vertically stretch this pink line, that means any point that's on the pink line will be twice as far away from the x-axis. So that point's going to be, this point's the same. In other words, if you vertically stretch 0, 0, you still are at 0, 0. But every other point on this pink line is going to be twice as far from the x-axis because I'm multiplying it by 2. Okay? So I end up a vertically stretched line looks like that. And that's the way to think about it. If that, instead of a 2 was like a 1/3, then every point on this pink line is going to be closer to the x-axis, and the pink line is going to be 3 times further away than whatever my new line is. So when you're thinking of vertically stretching or shrinking, that's how to think about it. Is just instead of trying to picture what a vertical stretch of that pink line looks like, just take a couple of the points that are on the pink line and make them twice as far away from the x-axis. And then connect the dots. And finally, the blue line will be my final function. What do I do with the green line to get the final function?
It's a vertical
What is it? A vertical what?
I forgot, but
The two was a stretch, right? So the +1 cannot be a stretch or a shrink. So the other word is shift.
shift, yeah.
The 3 words you have to remember, and it's complicated because they all start with S, or SH, or ST, are stretch, shrink, and shift. The thing to remember about shift is it does not change the shape. The 2 was a stretch, and that did change the shape. The green line is not the same shape as the pink line is. But when I go from the green line to the final line, all I'm doing is taking the green line, moving it up exactly 1 unit, every single point on it. There you go. And so this point is on the curve, 0, 1. And you could plot a bunch of points to figure out how to graph the blue line. You wouldn't have to do it by these transformations. In other words, if I just take this function here and make myself a table of x, y points and plot those dots and connect them, I'll get that blue line. I don't have to know anything about transformations. Sonny, make up your mind. Come on in. Sorry, my dog's wanting to go in and then out and in and out.
Oh, it's okay.
Okay. So there are multiple ways to graph all functions. And by far, the most basic of all is just make an x and y table. Just like I did before. There's the x value, there's the y value. If x is 0, what's y?
0?
Plug it in. Plug it into this function here.
Oh, it's 1.
Not the parent function. In other words, I'm trying, if I gave you this function and you did not know anything about transformations, you could still graph it by just making an x and y table. So if I plug in x of 0 there, what's y?
1.
That's why that point is on the graph. If I plug in an x value of 1, what is y?
-1?
Good. That's why that point is on the graph. 1, -1. So you see what I'm doing? In other words, with an XY table, I can get myself a collection of dots. And all I need to really know is the general shape of this function, and I can connect the dots with that shape. But that would ignore this category of transformation of graphs. And they want you to learn about transformations of graphs. And this is a big topic. This truly is. You might spend a week on this in class. You might actually have like 4 hours of transformations of graphs. Okay? But I think you have it pretty good. I think you got it down pretty good. I'm going to give you one more. And this is a tougher one. Not really. It just looks like a tougher one. What's the parent function?
Y = x?
What 3 things are going on?
There's a vertical reflection over the x.
Okay. There is the original graph, just a linear graph, a straight line. So I've got a reflection over X. And if you don't know what that looks like, let me draw it in red. That's what a reflection over X looks like. In other words, every point that's on the black line, just put it in equal distance in the bottom right quadrant on the other line. And the 3 is what?
It's a vertical stretch of 3.
Yeah.
Of the factor of 3.
And if we're familiar with our linear functions, that's the slope also, right?
Yeah.
What's the slope of the original parent? What's the slope of the parent function? 1. So whatever that coefficient in front of X is. If I gave you a function y equals 2x, the slope is 2. Okay? In this case, the slope is minus 3. Well, we know slopes, that's steep. Okay, so if I'm going to draw that, it's going to look something like this. It's still negative, but it's steeper than my pink line. Because that's what when you do a vertical stretch of a straight line, you really are just increasing the slope. And then the plus 4?
A vertical shift of 4.
Okay, which takes that point right there and puts it right there. So now I draw that same green line, only I've shifted everything up by 4. All right. I think you understand transformations pretty good. You feel like you do?
Yep.
Can we go on?
Yep.
Okay. We'll review all of these at some point, but we got to keep going. These other topics here are not that, they're not as big as, we can cover the next 6 topics in the same amount of time that we did transformations, I believe. So let's talk about finding X-intercepts. If I give you a function, how do I find the X-intercept?
I've forgotten.
What's the Y value on the X-intercept? Always.
1.
0. In other words, no matter what function I am drawing, I can draw a real complicated function like that. Okay? There's one X-intercept, there's another X-intercept, and there's a third X-intercept. What is true about all 3 of them? What's the Y value?
0.
What's the X value when I'm looking at the Y-intercept?
It's like 3-ish.
That's the Y value. What's the X value?
0.
Yeah. So whenever you're talking intercepts, if you're talking about the X-intercept, the Y is 0. If I'm talking about the Y-intercept, the X value is 0. Okay? So, how do I solve for, let's do the easy one first. What's the Y-intercept?
0.
Plug in 0 for X and figure out what the function is valued when X equals 0.
4.
Okay, that's the Y-intercept. That's always how you get these intercepts. And the Y-intercept is usually easier to solve because usually you have a function that's Y on the left side, all the X's are on the right side, and plugging in 0 for X becomes a very easy thing. Just crosses that term out. So you're left with whatever that constant is. Figuring out the X-intercept is a little harder because I've got to set Y equal to 0. Well, if I set Y equal to 0, this is what I have. With me?
Yep.
Solve that for X. That's going to be our X-intercept.
4 again?
Solve this equation for X. Isolate X on one side. That means you got to get rid of the plus 4 and you got to get rid of the minus 3. How do I get rid of the plus 4?
You subtract 4.
Okay, so that's the next line. Now how do I get rid of the minus 3?
Divide by -3.
So it becomes that. The two negative signs cancel. And that is my X-intercept. Okay? But notice that the X-intercept was harder to solve for than the Y-intercept. The Y-intercept is usually, it's usually whatever that constant is, that's the Y-intercept. And it doesn't matter whether this is X squared or what. In other words, if you can set X equal to 0, it usually eliminates all terms but the number. So you're staring at the Y-intercept usually. The X-intercept requires you to do a little algebra, but very little. Because all you have to do is set Y equal to 0. Okay. Give you another. Hold on a second, I'm not sure that's what I want. Think for a second. All right, we'll deal with this one. What's the parent function?
It is y equals x squared.
Yeah, you didn't really need to know that. I just was testing you.
Okay.
Now, what is the Y-intercept, the easy one?
It is -4.
-4 squared. Right? You see why?
Yeah.
In other words, if I plug in 0 for X, I got -4, but I still have to square it. And -4 times -4 is plus 16. Now, what's the X-intercept? Give me the equation I need to solve.
It's 0 equals parentheses x minus 4 squared.
Okay. How do I solve that?
You would do the square root first.
Square root of both sides. What's the next line?
0 equals x minus 4.
And the last line?
It would be 4 equals x.
That's the X-intercept. Okay? So
Okay.
finding intercepts is relatively easy. If you're looking for an X-intercept, you set Y equal to 0. If you're looking for a Y-intercept, you set X equal to 0. No matter the function, no matter how complicated it is or anything else about it. So let's go to vertex form. First of all, let's talk about standard form. And when they're talking about these, they're talking about quadratics. In other words, you're not going to really get very much into cubics or square root functions. What you're going to deal with mainly in Algebra 1, or I know you're taking geometry, but the things you have to be familiar with from Algebra 1 are really linear functions and quadratics, where there's a squaring going on. Okay? So standard format of a quadratic is y equals ax squared plus bx plus c. Something like the following. Y equals 3x squared plus 2x minus 7. That would be a quadratic in standard format. Okay?
Okay.
Now, I know that's a parabola. It's just, I don't really know how to graph it very easily. I mean, I could do my XY table, but that's really a last resort method. You're better off figuring out how to graph these by a method other than an XY table. Okay? And that's why this vertex format is very important. This is standard format. Vertex format looks like this. And it's also a quadratic. The vertex format of a quadratic looks like where H and K are the vertex. In other words, that's why this is a great format. If I gave you an example of vertex format, it might look like this. Where's my vertex?
It would be -2 and 5.
Not -2. Notice that the standard format is x minus h.
Oh, so then it would be 2 and 5.
Yeah. So 2 and 5 is right there on my graph. I know it's a parabola. It's open up or open down?
Open up?
Yeah, because it's a positive in front of it. +3. So I can do a pretty good job of graphing it just by knowing where the vertex is. Okay, now I can't say that that's an accurate graph because I didn't apply the vertical stretch factor of 3, and I did apply the shift. In other words, the shift is taken into account by where the vertex is. But you'll notice we're looking at this kind of a parabola that's been shifted to the right by 2 units and up by 5 units. Okay, so vertex format is a terrific format in that it allows you to graph it very, very easily. Whereas standard format, you need to do quite a bit of algebra to graph on standard format. And I don't even see anywhere in here where they talk about standard format. They do talk about intercept format, and we'll talk about that also. Intercept format looks like this. There's 3 formats for quadratics. That's x minus p times x minus q. What do you suppose p and q are?
The intercepts?
Exactly. And you'll notice that most quadratics, parabolas that is, are going to have two intercepts. In other words, a typical quadratic looks like this. Okay? There's an intercept right there, and there's an intercept right there. That's P and Q. So if I gave you a quadratic in intercept format, might look like this. And the intercepts would be at 3 and 4. Okay, so if I was going to graph it, I would go to 3. Graph it. Start. I would, first of all, find 3, find 4. Now I got to draw a parabola that goes through both of those, like that. Okay, so intercept format is also an extremely valuable format to have in order to graph the parabola. Now, look at the difference between these three formats. That's standard format. That's intercept format. And an example of vertex format would be something like this. So if you have it in vertex format or intercept format, pretty easy to graph. I'm not sure. Let's see. Let me think for a second. What else I need to add to these subjects here? Vertex format, intercept format. There is a method where you can take whatever format you're given. Let's say they give you the quadratic in standard format, and you can convert it to vertex format or intercept format. And the idea behind converting it is that you can turn it into something that's much more easily graphed. In other words, it's difficult for me to graph this quadratic when it's in standard format. I can do it, but I don't see standard format on this list, so I'm reluctant to even get into that. Whereas they do have vertex format and they have intercept format. And I believe you can kind of get an idea. The vertex format, you always, whenever you're graphing a quadratic, a parabola, you're going to start at the vertex. That's really where you want to start. So the best format to have a quadratic in is vertex format, because you can immediately find that point right there. In my example, that is 3, 7. Okay? Intercept format is relatively easy to, and what is the A? That's the vertical stretch factor. So once I know the vertex, and I know that, gosh, this is a parabola with a vertical stretch factor of 2, I know it's going to be skinnier than the average looking parabola. So I made it look skinnier. Now, the one thing I don't know about are what those two intercepts are. I didn't really figure it out. So I can't say that that graph is perfectly accurate. But I know where the vertex is. And that's the most important thing. Now, if you get something in intercept format, you don't know where the vertex is to start with. But you do know where it crosses the x-axis. You know these 2 points right there. And let's talk about symmetry, because I see down here axis of symmetry. The axis of symmetry is the imaginary line that goes through vertically such that this thing is symmetrical on each side. Okay? Well, in the function I've given you down there, that point is x coordinate of 3, that point is an x coordinate of 4. Where's the axis of symmetry?
It's the vertex.
It's halfway in between those two intercepts. It's at x equal 3.5. And it is the equation of a line. Notice that a vertical line's equation is x equals some number. Horizontal lines are y equal some number. But when you're talking about axis of symmetry, then you're talking about a vertical line. And you see why it's symmetrical about that vertical line?
Yeah.
And that axis of symmetry is always exactly halfway between your two x-intercepts. So if you're given something in intercept format, down at the bottom there, then you know where to put the x-intercepts, and you know how to find the axis of symmetry. And the axis of symmetry gives you the x value on the vertex. So I can figure out that the x value is 3.5. If I want to figure out the y value, I plug 3.5 in for x, and whatever the y value comes out to be, that's what it is. Well, in this case, I would have 0.5 times negative 0.5, which is negative 0.25 times 2 is negative 5. Negative 0.5, excuse me. So the y value for the vertex is minus 0.5. So even though I've got the function in intercept form, I can still graph it very accurately and very easily. I graph my two intercept points. I go halfway between them to find the axis of symmetry, which is the x value of my vertex. Plug that into the equation, figure out what y is. That's the y value of my vertex. And now I have the vertex and I have both x-intercepts, which means I can graph it perfectly. Because all you need is 3 points to graph a parabola. Any 3 points define a parabola. Hold on, my dogs are restless again. Hi, you want to go out? Hi? You want to go out or stay in? All right. Not a whole lot more to really talk about on vertex format, intercept format. If it's in standard format, there's a technique to figure out how to find the vertex, but I'm not going to go into it because it's not on the list here. What time are we looking at? We got about 10 minutes, okay. So we've covered that, we've covered that, we've covered that, we've covered that. Domain and range. We've also covered vertical stretch and shrink. We've covered axis of symmetry, and we've covered the vertex. So we've covered a lot now. The only thing we haven't really talked about is domain and range. And this is a pretty big topic. Let's take some functions. This is a linear function. In other words, what's the basic format for a linear function? Y equals what?
X.
Actually, it's y equal mx plus b. The parent, you are right, the parent function is y equals x. But what that means is m is 1 and b is 0. Okay?
Okay.
In this function, what is m and what is b?
2 and 1.
Okay, that means the slope is 2, the intercept is 1, it's easy to plot when it's in y equal mx plus b format. Now, let's talk about domain and range. Domain are all of the allowable values you can make x. In other words, whenever you have a function, you can make x anything you want. Hold on a second. As long as it doesn't violate any rules. Is there any number that I can plug in for x that violates any rules of mathematics?
A negative number?
No, I can put in a negative number. I could use -3. In other words, if I wanted to put in -3 for x, that's perfectly legit. The answer is y would equal -5. Okay? In other words, I can plug in 0. I can plug in any size negative number you want. I can plug in any size positive number you want. So the domain for this function is all real numbers. And you can write that in various ways. One way to write it is that. Another way to write it is from anything from negative infinity to positive infinity is allowable. Okay. Now let's take some functions where the domain has some restrictions. In other words, that function right there has no restrictions on either the domain or the range. And I want to talk about domain first. What if I gave you this function? What are the allowable values for x?
Negative numbers, positive numbers.
Okay, so let me
Decimals.
be more. Really, the proper way to think about domain is not really to figure out what the allowable numbers are. It's to figure out what you cannot put in there. There's only one number you cannot have x be. What is it?
0.
Correct. So the domain for this function would be all reals except x cannot be equal to 0 because you cannot divide by 0. That is pretty much the first rule of mathematics. There's no division by 0. Okay? So the domain I could also write, if I want to write it, as -infinity up to 0, but you can't be 0, in combination with 0 to positive infinity. In other words, this says the same as that. It's just different notation. This is called interval notation, where I have the union sign there. But notice that it covers all the same numbers. And it does not, because I have a parentheses here, it means I cannot let it be 0. Okay, let's talk more domain. This function. What's the domain?
All real numbers except 0 again.
It can actually be 0. You can take the square root of 0. 0. What can you not take the square root of?
Negative numbers.
So here the domain is x has to be greater than or equal to 0. It cannot be negative. Okay? Now, what if I gave you this function? What's the domain?
All real numbers except.
When you have something inside the radical sign that's a little more complicated than just x, take whatever it is and make it be greater than or equal to 0, and then solve that inequality. That means x has to be greater than or equal to 1. That's the domain. In other words, notice that x cannot be 0. If x were 0, I'd be taking the square root of -1. You can't do that. X cannot be 1/2. I'd be taking the square root of -1/2. But x can be 1, and x can be 2, and 3, and 3.5, and 1,000,000, and 1,000,000,000. So it's all you have to do is take whatever's inside the radical sign and make it greater than or equal to 0 to figure out the domain for square root functions. Okay, let me get a little harder. About that one.
All real numbers except negative numbers?
Almost. Can x be 0?
No. So all real numbers except negatives or 0?
Yeah, and the way you want to write, the easiest way for you to write it is x has to be greater than 0, not greater than or equal to. Because in this particular case, x cannot be equal to 0, because I can take the square root of 0, which is 0, but then I'm dividing by 0, which I can't do. So x in this case has to be greater than 0, not just greater than or equal to 0. Thinking up other good ones. I think let's talk about range. Range is the y values. Domain are the x values. Range are the y values. Okay?
Okay.
We've already determined that when you have a linear function like this, the domain is almost always all real numbers. In other words, there really are no restrictions on x. X can be negative, x can be 0, x can be positive. Okay? What's the range? What are the allowable values for y? In this case, it's all real numbers. And range is much harder than domain. Figuring out the range is harder because it's more difficult to see. In other words, I can tell immediately that I can plug in any value I want for x. The question is, can I create all values for y? Well, let's draw a quick graph of this function. Goes through -3, has a slope of 2, so it looks something like that. Now, if you look at the graph, you can see that the domain is all real numbers, right? In other words, I can put in any number I want, as big negative as I want, and I can put in any positive number I want, as big a positive number as I want. I can also see from the graph that I can get any range. In other words, it goes all the way down to -infinity, it goes all the way up to positive infinity, and there's no points in between that are missing. So from the graph, I can tell the range is all real numbers. Now, figuring out the range algebraically, it's a little harder. I tell you what, it's 8 o'clock. Let's put off more discussion about range until our next session.
Okay.
Okay? Because it's a little more complicated, and I know there's a certain amount of burnout that occurs at the 1 hour level, so we'll start out the next session on range. All right?
All right.
You have a good rest of your weekend, and I will probably talk to you next week.
Yep, sounds good.
Okay, bye-bye.